Hi guys, welcome. Let us proceed with the next question in the graph algorithms collection. Round trip. Byteland has n cities and m roads between them. Your task is to design a road trip that begins in a city, goes through two or more other cities, and finally returns to the starting city. Every intermediate city on the route has to be distinct. All right. So this question basically asks you to find a cycle within a graph, and the cycle must contain at least three distinct nodes. So goes through two or more cities. They give an example here, which we are going to take a look at. Now, you also need to print the cycle when you find one. So this question would have been pretty straightforward to solve, but the fact that you also have to print the cycle makes it a bit tricky. So let's look at an example and see exactly what is being asked of us. All right, so this is basically the first example they gave. So 1 is connected to 3, to 2, 5 to 3, etc. So that is basically what I've represented here. And there are a couple of cycles in this graph. This is one of them. All right. The entire set of nodes also form a cycle, and also this is another cycle, which is indeed the example, the answer they went with. So 3 to 5, 5 to 1, and 1 to 3. So we'll have 3 to 5, 5 to 1, and 1 to 3. Okay. So that's the question. To solve this, you want to take note of two things. First, you can use depth first search to find if the graph does indeed contain a cycle. So use DFS to find the cycle. Okay. Secondly, because you need to print out the path, you also need to keep track of nodes in the DFS path. Okay, so once we can do those two things, we can easily solve this question. So we're going to look at three different examples and see how it works in practice. So for this example, we're just going to use a stack to keep track of the nodes we visited during the depth first search exploration. Of course, we also need a different kind of set to keep track of nodes we visited, like a Boolean set. But this is for the path, okay? So we start from node 1 all the way to the last node. So here, we are currently at node 1. We run our depth first search, and from here we go to 3, okay? From 1, we try to visit the child, which is 3. So we add 1 to this. So at 3, okay, we can ignore the parent, which is the node that from which we came to our current node. So we are right here at 3. Then we look at the children, so we're going to look at 5. So 3 goes into our list. Now we move to 5. Okay, so now we're here. And 5 goes into our list. Of course, we can also, from 5, we can go to either 4 or 1 because those are the children. So now let's go to 1. Aha, we see that we've already visited 1. At this point, we can compute our answer and return. So since we've already visited 1, we simply, first of all, we're going to print the node, and then we print all the nodes moving backwards until we find the node we started with. So in this case, 1. So we're going to go 1, 5, 3, and then 1. And that will be the answer. Okay. So maybe another example would clarify things. Let's take a different example. Okay. So as always, we start with the first node, 1. Let's open our array to keep track of nodes we are currently visiting. So we have 1 in this array. We look at the children, which is 2 and 5. Let's go to 2. All right, so we add 2 to this. We look at the children, which is 3. We can't go to 1 because that is the direct parent. You're going to see how to avoid that in the code. So we go to 3. All right, so we add that to the list or stack. We look at the children, which is either 5 or 4. So for this example, let's go to 4. Okay, so we are here. So we add 4. We look at the children. It has no children. Of course, we can't go back because that is the direct parent. So we are done exploring 4. Okay, when we are done with a particular node, we have to remove it from the stack. So since we are done with 4, let me use another color for it. We are done with it. So we now remove it from this stack. Okay, and continue to look at the children for 3. So the next child for 3 would be 5. So we move here. So let's add 5 to that. Okay. And then we look at the children for 5. We have 1. So we move to 1. All right. So 1. As you can see, we've already visited 1. So at this point, we can print our result. So we just print from this all the way till we find 1 once again. So we have 1 to 5 to 3 to 2, then finally to 1. And this would be our answer. All right, so let's quickly look at an example where we did not get any valid answer, in which case we have to print the word impossible. All right. Okay, so once again, we maintain our list and start our depth first search. So from 1, we go to 2. From 2, we go to 3. So at 3, it has no children. We are done exploring. So we remove that from the stack. Okay. We go back to 2. We are done exploring 2. All right. So we remove that from the stack. We go back to 1. We are also done exploring 1. So we remove that from the stack. All right. So we just keep looping 1, 2, 3. We've all seen those nodes. So we come to 4. So now we are here at 4. We add that to the stack. From 4, we go to the child, which is 5. Add that to the stack. 5 has no other children, so we are done exploring 5. So we remove that from the stack. And finally, we go back to 4. We are done exploring that. We also remove that from the stack. So at this point, we've basically explored all the nodes, and still we could not find a cycle. So in this case, we just print impossible. So that's the basic idea of the algorithm. You can pause this video and try to code it out yourself, but let's discuss the time complexity quickly. So this is going to be a linear time algorithm. Depth first search usually is linear time because we just explore the nodes and keep track of the ones we've seen, so we don't have to explore them over and over again. The space is also linear because we're also going to keep track of certain things like the nodes we visited and also the stack that contains the path we are currently exploring. So that's it. Next, I'm going to code out the solution. All right, let's create a class called round trip. For solving the problem. Okay. So the first thing we want to do is to read the input, and then we're going to find a cycle in the given graph. Okay. If we are unable to find a cycle, then we're going to print impossible. So let's create this variable called found. Set it to false for now. If we are unable to find the cycle, then we're simply going to print impossible. All right, so that's the basic shape of our algorithm. So let's try to define some of these. So the first thing you're given is n and m. N for the number of nodes and n the number of edges between them. Or in other words, the number of roads, which is same as edges. So let's have that, and then an adjacency list. Okay. Now let us define this function. It's quite straightforward. We're just going to look through. We're just going to read in the input given n and m, and then loop m times to set the adjacency list. Okay, so that's for reading the input. So next, we're going to define this find cycle function. So what this does is basically to find a cycle within the graph. All right, so to do that, we need a couple of variables. So we need a Boolean list to keep track of the nodes we've already visited. All right, so you're going to see how we use that in our depth first search algorithm. Okay, so let us initialize visited. All right, and then we're going to loop through each node. So if you've already visited it, you can just continue. Otherwise, let's create this path, which will keep track of the path we're currently on, and then we're going to run DFS for that node. All right, so let me define depth first so you understand what each parameter means. So the next is the parent, and then finally we have a reference to the paths. Okay, so that's basically the definition. Now, if we've already found a cycle, we don't need to explore further, we could just return. Okay, now, next, if you've already visited the node, that means that within this depth first search exploration, we have a cycle. So you visited node, then you have a cycle. Okay, so what do you want to do if you have a cycle? If the path size is greater than 2, then we've met the condition that you should have 2 or more cities. So basically, you're just going to print the result and return. Okay, so I will define this later, but for now, once you've done this, you've handled the case for when you have a cycle. Let's just finish up the depth first search function. Okay, so what you want to do is to set the visited variable for the node to true. And then add the node to the path. Okay, once you've done that, then run depth first search for the children and then remove the node from the path. So it's a bit like backtracking. Of course, if the child is the same as the parent, you just continue. Okay, then you remove the node from the path, and that's it. This is your depth first search function and it should work. So finally, let me just define this print results function, which is pretty straightforward. So this takes in a reference to the path you have, and just like you explained, the first thing you want to do is set the found variable to true. So this is the found variable which you're going to use to decide if whether or not to print impossible. Okay, so the rest is pretty straightforward. So you just count the number of items in the path, and then add those to a string. Once you're done, you can just print it out. So that's the basic algorithm. Let me initialize this and run it. Okay, so let's try with the example they gave. All right, so you have 4, 1, 5, 3, 1, just like I explained. Just like I explained right here. I mean, there are other ways to implement this, but I just try to break it down so you understand what each function does. All right, so that's the solution. Let me try to submit. All right, so that got accepted. Thanks for watching.